Yves Vanbrabant is a senior geologist at the Geological Survey of Belgium since 2004. He is specialized in structural geology and geodynamics, and the subject of his PhD at the University of Liège, Belgium, was focused on the geodynamic evolution of the eastern part of the Ardennes during Variscan orogeny. His main role at the GSB since 2004 is that of project leader, and in 2015, he has also taken over the direction of the survey. His main research and service activities at GSB involved the sustainable management of raw materials and different projects related to the development of geothermal energy in Belgium. Some of these activities are conducted in collaboration with regional authorities. Yves is also extensively involved in different EU projects, and in the framework of the MIT project, Yves and his team are in charge of the research activities related to the avalanche demosite. The title of Yves' lecture is The Role of Anisotropy in Geothermal Systems in Meta-Sedimentary Rocks. Please, you can go, Yves.
Okay, thank you, Beatrice. Can you see my PowerPoint?
Yes, very well.
Yeah, okay, great. Just one point is, you mentioned that I'm the director of the survey. I'm very happy to say that I'm not anymore the director of the survey, and I'm fully back to as a full-time researcher in the survey, and I'm a happy guy.
Great.
Okay, thanks for this introduction. First of all, I would like to say that I have, and I hope you will not mind, I have slightly changed the title of my presentation, because I start my presentation from scratch, and so you know when you're preparing a PowerPoint, a new idea comes. So I had a debate with my partners, who is also a geologist, and about anisotropy, and I was not fully happy with some points. So because in some cases, do we speak about anisotropy or heterogeneity? So the content of my presentation today will be, first, I will quickly present you the demo site of Avalanche, the site that we are working on in the MIT project context. Then I will speak about anisotropy and heterogeneity in a more global sense. Then I will obviously focus on anisotropy in geology. We will study two cases about thermal conductivity, anisotropy of the thermal conductivity, and in rock fracturation in meta-sedimentary formation. And then I will, because I think in the planning I'm the last one before lunch, I will give you a takeaway message. So you have, I think, probably see this picture several times. And I think Bern will probably present it once again this afternoon. In the framework of the MIT project at the Geological Survey of Belgium, we are working on the northeast corner or northeast quarter of this ellipse. So it's the Ardennes. We are working in Belgium on the avalanche demosite. So we are clearly in the Variscan meta-sedimentary contexts. And in Belgium, there are not that many post-Variscan extensional tectonics. So what we observe is mainly the result of the Variscan orogeny. In this site, we are studying on different aspects about old data, new rock samples, either from the avalanche boreholes or even collected in the field. So a quick overview about the avalanche boreholes. So you can see it's the avalanche borehole is located at the red dots in Belgium, so close to the village of Nettin. It's a pretty old borehole that was drilled from 1981 to 1984. So that took about 3 years to drill, because it was a very complex drilling site, especially the drilling of quartzite. At the end of the boreholes reach a depth of 5,648 meters with the depth. The initial goal was to drill to 6 kilometers, but the budget was completely spent after more than 5 kilometers. And there was a big problem with the drill bit, so they have decided to stop the drilling at 5,600 meters. The initial aims of the boreholes was gas exploration, targeting upper Carboniferous core measure under the main detachment level, which is called the mid-thrust. So, as I mentioned, the target was to find upper Carboniferous core measure, but the boreholes never reach or never encounter upper Carboniferous formations, and we had only formation from the upper to lower Devonian formation. So in terms of global tectonics, the avalanche borehole is located in what we call the Dinant synclinorium, which is a subunit of the Ardennes Alloctone. The Ardennes Alloctone is also a part of the Rhéno-Estonian fault and thrust belt, and everything is in the Variscan orogeny. So the site is located 23 kilometers south to the Variscan front. And in the framework of the MID project, we studied these boreholes, not for a perspective of gas exploration, but for geothermal targets. In our case, our targets are the lower Devonian quartzite unit observed between 4 kilometers and 5 kilometers. At the bottom of the boreholes, the temperature that was recorded was 126 degrees. The boreholes in 1985 was sealed for protection, because even if the gas production was pretty poor, there was some risk of gas accumulation. So we have decided to seal the boreholes, but it was still as a petroleum well, so it can be reopened, but needs specific techniques. So regarding the information that are available regarding these boreholes, we have a lot of cuttings with samples every 1 to 5 meters, that depends on the formations. We have also cores at shallow depths in the Flaminian Shale and at greater depths, mainly in the lower Devonian quartzite. We have many logs, but all of them were in papers format. So during the MID project, we have digitized the most important one for us. So it was gamma ray, deep meter sensor. Besides the avalanche boreholes, 6 seismic lines were shot in 1978. During the MID project, we have collected new information. We restudied the mineralogical composition of some cuttings and cores, and we restudied the daily drilling report, especially the mud loss, to get information about fluid circulation. In the near fields, so it's the area near the avalanche boreholes, the main activity was quite limited, but we at least made some imagery by drone during the drought period of 2018. We also collect spring samples, water from springs in the near field, but also in the far fields. In the far fields, we collect new rock samples for the rock mechanical tests conducted by our colleagues in TU Darmstadt and in Potsdam, and we study some outcrops. So you've got here on the left-hand side a cross-section through the quite old cross-section. We should come with a new one. You can see the avalanche borehole, sondage, so boreholes in French. That was quite deviated, and you can see that the boreholes crosscut first the upper Flaminian and then Franian limestone, Giversen, and then reach middle Devonian and lower Devonian formation, which consists mainly of shale, sandstone, and quartzite. At the lower part of the boreholes, there are some indication, but it's not very clear, that the borehole has probably cross-cut the main detachment fault that I called previously the midi-thrust fault. But the situation is rather complex, and on both sides, above and below the main thrust, we have lower Devonian formation, and they are quite monotonous with quite limited amount of available criteria for separate one formation to the other one. On the right-hand side, you have a geological map of the area near the avalanche borehole. So the avalanche borehole is represented here by the yellow circle. We have defined it a near field just 5 kilometers around the avalanche boreholes. And we are studying what we call the analog area, so the far field, where we can see here the lower Devonian formation that we have encountered at greater depths in the avalanche boreholes. So let's finish with the avalanche description. Let's jump on anisotropy. So what is anisotropy? So I took the definition of Wikipedia. The definition seems a bit more complex than I was expecting, but at least we have a definition. Anisotropy is the property of a material which allows it to change or assume different properties in different directions. Obviously, anisotropy is the reverse of isotropy, where a parameter has the same value in all directions. So in the simplest case, anisotropy in 2D can sometimes define it as the ratio of the parameters that we want to study in the direction where it presents its maximum value on the usually perpendicular direction, which exhibits the minimum value of these parameters. So in that case, we can present the anisotropy as a 2D ellipse. But obviously, if we jump in 3D, we have ellipsoid. For isotropy, it will be represented as a circle in 2D and as a sphere in 3D. But in other cases, the anisotropy can be a bit more complex. You can see here for magnetism that the anisotropy can be even quite complex, and for fun, can have even weird shape. So as I said, when I start to prepare the PowerPoint, I was not that happy simply by just discussing about anisotropy, because I think we need also to look at heterogeneity when we are speaking about such properties. So I like this diagram because it represents on the left column the anisotropy, and on the right column the isotropic properties. Also, if you look at around the row, we can make a distinction between heterogeneous systems and homogeneous systems. So if I take the first square, you can see that we can speak here about anisotropy, because if you look at the gray layers, it represents properties that are very different in one direction versus to the other. But you can see also that we have a distribution of different materials, so we have an heterogeneous systems. By contrast, here, if we look at what is isotropic systems, we can speak here about isotropic because the properties have the same value in the both directions, but it's heterogeneous because, as you can see, the matrix have values that are different from the properties for the, let's say, pebble or the phenocryst. Now, if we jump to the lower row, you can see that we have here some rocks that is anisotropic because the properties are very different in one direction versus to the other. but it's quite homogeneous. And the easiest case is a material that is homogeneous and isotropic, probably such as glass. So now, if we jump to anisotropy in geology, anisotropy is present in many geological settings at different scales and for several properties. If we look at some anisotropy for rocks, we have many examples of anisotropy that can be the mineral plasticity, elasticity, fabrics, sonic, electric. But, and I'll let you read, obviously, but we have also thermal conductivity and permeability. An important point, I think, when we speak about anisotropy is also to speak about the scale. In some cases, we speak about single crystals, someone that study at the microscopic scale, to the field geologists that study a full geological sequence. The anisotropy also in a geological cycle can happen in different periods. It can be a primary anisotropy, like the formation of sedimentary formation, or a secondary anisotropy during a tectonic process, like the development of a cleavage. So why is it important to study anisotropy? And I will say, when we study anisotropy during modeling, I really like this picture because that represents, it could be a very takeaway message for the young student that wants to study geothermal systems, especially in modeling. If you look at the picture on the left-hand side here, you can see we have schist materials, and here it's a quartz vein, and this quartz vein has been folded. If you look at, you've got the scale with the coin. This quartz vein is in this matrix, and this matrix exhibits a first cleavage, S1, and a cleavage. This outcrop has been used as an example to study the buckling of a single layer, a competent single layer, within an incompetent matrix. On the right-hand side, you can see the result of 4 different models. So the two models at the top, B and C, represent the result of the numerical modeling of single layers in an incompetent matrix, with 2 different approaches, with a model in simple shear and the other one in pure shear. As you can see, after a significant amount of deformation, we reach a folding of the competent layers, quite similar to what we observe in the field. But if you look at in the matrix, you can see here, it is represented as a series of passive markers, that the folding this decrease very quickly far from the competent layers. And it's even worse in the case of a pure shear. So those models were done by considering simply isotropic rheology. So that means when the model was introduced, the properties of the matrix and of the competent layers were isotropic, so the same behavior in all directions. To achieve the folding also for such a models, we need to trick a little bit the systems by inducing a variation of the thickness of these competent layers to initiate the folding. Otherwise, we have simply a shortening and a thickening of the layers. By contrast, more recent models that consider a modeling with anisotropic rheology provide a quite different result. We have the same type of folding, but also you can see that the folding is not do not decrease as quickly as in the isotropic models. And also we can see here the development of crenulation cleavage. I saw a big difference between the models with isotropic rheology versus the model with anisotropic rheology is to achieve the deformation, the folding that we want. The simple shear and the pure shear were more important than in the case of anisotropic rheology. So that means probably that in those cases, the deformation is overestimated. So I don't know how to proceed exactly, Beatrice, or Xavier, could you help me? I prepare some sort of exercise. Is it possible or not?
Oh, yes, sure.
Sure.
Good idea.
So first, the first study case is about the thermal conductivity and isotropy. So as a reminder, when we speak about geothermal systems, we are interested by the heat transfer mechanism that are conduction, convection, or even radiation. For this case, I will just focus on conduction. So if we consider a very simple approach, or 1D approach with the Fourier law of heat conduction, we can, so it's taken from literature, from Turcotte and Schubert. If we consider a slab of rocks, which has a thickness of L, and one side is hot and the other side is cold, we could evaluate a heat flux from the hot to the cold side. So the heat flux is represented by Q, and it's expressed in watt per square meters. The equation is pretty simple because Q equals K times the difference of temperature between the hot and the cold side divided by L, the thickness. So K is the thermal conductivity, which is expressed as watt per meter per Kelvin. And for rocks, the value, let's say for a shell, is around 1, or perhaps in some cases a bit below. And other rocks like dolomite and magnetic quartzite, the thermal conductivity can be pretty high, above 5. The K value can be measured in labs or directly in boreholes conditions. So for thermal conductivity, we conduct such a tests in our survey. We have acquired an equipment called thermal conductivity scanning or scanner, TCS, and you've got a picture of the equipment. So the equipment is composed of a metallic frame with 2 plates and a slot in the middle. When we want to study the thermal conductivity of our rock samples, because we are a survey, we are frequently working with cores, we cut the cores in half, and we put the half core on the metallic frame between 2 blocks, the black blocks here, that represents standards for which we know the thermal conductivity. The results are acquired thanks to a blocks, which is located here, that slide from the left to the right. So this block, the moving block here, is composed of 3 things: a cold sensor, a heat source, and a hot sensor. During a measurement, the block moves, as I said, from the left to the right. And why do we have a cold sensor and hot sensor? Is simply because the hot sensor is will conduct the measurement before the heat source. So when the block moves, the heat sensor measures the temperature of the first standard, then the samples, and then the second standard. Just behind the first sensor, we have the heat source that will heat the standards, the blocks, the core, and the second standard. And then we have the third component, which is the hot sensor that measures the temperature of the standards after heating, and the core and the second standard. So you've got a result of what we can see. So here in blue, it's the result of the cold sensor. You can see that, so the horizontal axis is simply the displacement, and the vertical axis is the temperature. As the samples, the block move, we record the temperature of the first standards. Then we have a gap between the first standard and the core. We have the temperature of the core, the samples, before to be heated, and then the second standards. After that, the heat source heat the samples, and we record the temperature of the first standard, the samples, and the second standards. So you can see the jump of the temperature. Knowing the temperature, the thermal conductivity of the standards, we can evaluate the thermal conductivity of the samples. If the samples was homogeneous, we could expect to have a flat surface, and you can see here in this case, the samples is not at all homogeneous, but show pretty strong variation along its axis. So for thermal conductivity and isotropy, regarding meta-sedimentary formation, laminated rocks like shale, slate, conduct it preferably parallel to the bedding plane. So the key value is measured on the surface for such laminated materials in two directions, one parallel to the bedding plane, and we will speak about the thermal conductivity K par, and perpendicular to the bedding K per. K per is usually the minimum value. So Davis et al. Conducts many tests on different rocks, and they have seen that the anisotropy is between 0.8 and 2.1. And here, as I already mentioned, we can express the anisotropy as the ratio of the thermal conductivity parallel to the bedding on the thermal conductivity perpendicular to the bedding. Davis and al. Made also a test not only in two directions, not only in parallel and in perpendicular direction, but for a range of different angles. And you've got here an example of their results. We will focus on these samples. So the 9701, you can see that the thermal conductivity measure perpendicular to the bedding, it's has a value about 3, and parallel to the bedding plane has a value about, let's say, 4.4 around. So first, I would suggest that we try to apply the equation that is located here in the graph to evaluate the thermal conductivity, the apparent thermal conductivity with an angle of 40 degrees. So the angle gamma equal 40 degrees. So I suggest to use this equation. I don't know how the test will be done, but if you, as a reminder, if you use Excel, don't forget that Excel takes the angle in radian and not in degrees. Beatrice and Xavier, how can we proceed with that? I have the result to the next slide, so I will not I will not show the next slide, but I'll let everyone during 5 minutes, or I don't know what time is it. Yeah.
Yes, it is 25 to 12. Yes, 5 minutes is good.
I think for the first one, the first one is very quick. But
so maybe less than 5 minutes?
Yeah, 2 minutes, I think.
2 minutes.
That gives me the time to drink.
When you're done with the calculation, please put your answer in the question and answer box. And then we'll have the result given by Yves.
And I hope I have the good answer.
Two minutes are over. Who has an answer to the question raised by Yves? Nobody wrote anything in the question and answer box. Such a shame.
Okay.
Oh,
yeah.
yes, there is one answer.
Should we wait?
Oh, well, maybe we wait for another answer.
Yeah.
Who will give it? Don't be shy. You won't have a bad mark if the
No.
not the good one.
Perhaps you can even make a lucky guess.
No more answer. So Yves,
Yeah,
we'll
okay.
let you give the good one.
Beatrice, am I the only one to make such a quiz or questions?
Sorry?
Am I the only one to do that? Or
Yes.
okay. No, it's because I thought you wanted to have some interactive approach, but obviously it's not that easy with that many participants.
Well, there are many participants, 72 connected at the same time, but only one gave an answer.
Okay, so let's see. Oh. But my PowerPoint do not react. My PowerPoint is also shy. Yes. So the value that I computed was 3.67 watt per meter per Kelvin. Perhaps the difference with the answer of Raquel comes from the value that are taken from for the K min and K par. They can be slightly different.
Yes.
So I've prepared a second question, but perhaps I don't know if we have time.
So congratulations, Raquel. It was a good answer.
Yeah. The second question was, but perhaps I will keep the questions and I will give the answer directly. Is what is the impact on the K value if the heat flux occur perpendicular to the rock fabrics with respect to a flux occurring parallel to these fabrics? So we can apply the Fourier law. That is just, I have many things at the top of my screen, but in principle, you can see the equation located just here in the blue rectangles. We can make an evaluation of the heat flux in one direction and in the perpendicular direction. There are different approaches. You can perhaps directly make the ratio or the relative proportionality of the K value, or you apply the equations for the K value for a difference of, let's say, 3 degrees for a slab of a thickness of 100 meters. If we conducted that, we have two different values of heat flux. Parallel to the bedding, we have a thermal conductivity of 4.45 times 3 degrees for 100 meters, so it's 0.03. And the heat flux, it's 0.134. Perpendicular to the bedding, we have a thermal conductivity of 0.09. So if we compare the heat flux with the fabrics parallel or perpendicular to the bedding, we have a reduction of the flux of 33%, which is, I think, quite significant. Obviously, what we have done here, it's a very simplified approach in 1D. We have only considered it as heat transfer by conduction, but there are other processes, like convection and permeability. But if we speak about convection, we need to consider the permeability and isotropy. So we are back to anisotropy. But also we have to consider many things like heat generation within the samples. So you can see that the thermal conductivity and isotropy can be quite significant, but it's mainly for laminated rocks like shale and slate. If we consider rocks like granite, which is not too much, which is free from a fracture, the thermal conductivity is probably pretty close to be isotropic. And for highly anisotropic material like shale, it would be better to provide two values of K, one parallel to the bedding plane and one perpendicular to the bedding plane. So now I look at the time. Yes, it's okay. The second study case is the rock fracturation in heterogeneous and sequence with materials that are anisotropic. So the example that I will present you now come from the Belgian Ardennes. The lithology that we consider is mainly sandstone, quartzite, and shale or slate. For the geological settings, this rock, the lower Devonian rock sequence, there went first an extensional period during the basin maturation, and they underwent the metamorphism peak. Then the sequence were shortened during the various kind of orogeny. So what we observe in many locations in the Ardennes is the presence of quartz veins that affect the different rock formations. In terms of metamorphism, we reach the green schist fascist. So to study the outcrop, I had to look at the sedimentary sequence to classify the sedimentary sequence into 4 different categories. We have at the top here shale or slate units, where the shale represent the main lithology. We have only some sandstone, thin sandstone layers, or even lengths of sandstone. We have an example of slate here and a sandstone layer that is folded. The shale dominant unit is self-explanatory. Sandstone dominant unit is when the sandstone layer start to be the main lithology, but we can still observe thin layer of shale. And finally, the last sort of sequence that we can observe is the massive sandstone, where we have layer of sandstone on each other, simply separated by very thin layers of usually shale. So if we look at the fracture in massive sandstone units here, you can see that the quartz vein can go through almost all layers, but it's for this quite large quartz vein. If you look at now to the right here, you can see the green arrow point towards a quartz vein, but this quartz vein is strongly affected by the interlayers, and we can see the extension of this quartz vein in the above and in the lower layers, but clearly the quartz veins are thinner in the top and the lower layer in comparison with the quartz vein in the area with the green arrow. So if we try to put this observation into the figure that I have already presented, because we are dealing with a massive sandstone unit, we could expect to be with a material that is pretty close to be homogeneous. But this homogeneity is not perfect, and we have the presence of tiny anisotropic materials here. So we are close to homogeneous, but with a bit of component of heterogeneity. And simply these tiny layers have an impact on the fracturation. I will skip this one. And I'll show once again the fracture in a shale unit. You can see that in the shale unit, we have, sorry, it's a slate unit. It's composed, it's quite homogeneous. We have a nice cleavage, and we barely see anything else. And the fracturation is just limited to the sandstone layers with some more or less regular spacings. And the quartz veins are blocked at the contact between the sandstone and the slate. Just one single quartz vein extends within the slate unit. So if we look at the more sickle, I know it's sometimes people don't like the more sickles. I really like it because I think it's a very convenient and geometrical approach on a boring equation. And what the more sickle represents is it's a link between the normal stress and the shear stress. We have, I think most of you have seen this failure envelope that defines the differential stress, so sigma 1 minus sigma 3, which is required to have a failure to occur. From the contact between the Morse sickle defined by sigma 1 and sigma 3 and the intersection or the contact with the failure envelope, you can define an angle 2 theta, and the newly formed fracture develop at an angle theta with respect to sigma 1. So we have to divide this value by 2. There are two domains, the compressive domains and the tensile domains. Tensile stress condition can occur in rocks, mainly something that we could expect to be only compressive, but thanks to high fluid pressure, we can reach the tensile domains. So the second test, perhaps that could be easier for this one, is we have here 3 different observations, 3 different types of fracture, and I would like to see what is the relationship between the fracture or the outcrop that you can observe with the corresponding more circle. So the circle A is this one, B it's the big one here, and C it's between A and B. So I will give you some hints about the outcrop here. What you can see, I put the sketch because the photo is perhaps not that easy to see. It's composed of a series of layers. You can see the different colors of for each layers, and a series of quartz veins. Don't forget that these quartz veins were created before the folding. If we look at the second examples, the second is here represented by a series of thin quartz veins. Don't focus too much on those lines, it's sedimentary structure. And the third one is a reverse fault that is located, with, as you can see with my cursor, and with the arrow. So can we give 2 minutes to answer which structure go with which circle? Beatrice? Xavier? Can you hear me?
Yes, sorry.
Ah, okay.
Yes, sorry, excuse me. Okay, yeah, 2 minutes is good.
Yeah, okay.
Yeah.
We have to answer so far. Some more answers from the audience?
I see one answer.
Nice one.
Okay, let's jump to the answer.
Yes.
So if we look at the circle A here, it corresponds to the case of the second picture, the picture 2, because we have a pure tensile opening of the fracture, and that could happen only in the case where the differential stress is not that big, and we have high fluid pressure, and the fracture happen perpendicular to the signatory orientation. the angle 2 theta in this case will be 180 degrees. So if we divide by 2, it's 90 degrees with respect to the stress. The circle B here is associated with the picture 3, where we have simply a fracturation with the shearings, but in a compressive settings. Here it was in tensile settings. Here we are in compressive settings. So it's the B case. And the last circle, the C, between A and B, it's an hybrid situation where we have shearing, but also the opening of the fracture. So it's what we can see here, because we have the quartz vein, so it's a tensile fracturation, but we have also the offset of the layers on each side of the quartz vein. I will skip that. Yeah. And I will skip that to have a bit time of, if necessary, for discussion. So regarding my takeaway for lunch, I just quote the paper by Run that I mentioned earlier. For them, when we speak about modeling, it seems that there is one elephant left in the room that is still commonly overlooked or ignored in this numerical modeling, and it's anisotropy. So I think for the youngest, there is the takeaway message from that is, if you work with material like shale, slate, and so on, don't forget the anisotropy is probably one of fields that is not yet fully exploited and can provide you with very interesting new results. And that's it. Thank you for your attention.
Thank you very much, Yves, for this very interesting talk and the quiz. Not many answers, unfortunately, but I'm sure the students made the results, but were too shy to made the calculation, but were too shy to put their results on the question and answer box. Are there any questions? No, not for the moment. Okay, so may I ask one question, please?
Yes, please.
Okay, so you've shown the important role of the anisotropy for example, thermal conductivity, which is very different whether it is parallel or perpendicular to bedding. And do you think these anisotropy planes can be the fluid flow pathways?
Nikkei, no, if you consider the, for instance, the cleavage, because that represents the plane that underwent the maximum of deformations. So it means the permeability is probably lower in along these planes. On the other hand, it's Ben will probably speak about that to, because when we study the outcrops, we study a situation that was in the geological condition that, for instance, of an orogeny. Now we have to deal with settings that is different. The temperature, the pressure are different. The fluid content of the sedimentary formation are different. So perhaps the behavior can be quite surprising. But if I remember well, the initial tests when we think about reopening the cleavage plane as a path for fluid flow was not that great. The result were because there is quickly a flux of the materials that seal the preferential flow along the cleavage plane.
All right, but maybe also that depends on the orientation of this cleavage according to present-day stress field.
Stress field, yes, of course, yes, of course.
All right, and I think Ghislain wanted to add something. And maybe Ghislain, you want to make your comment by yourself, if Xavier allows you to speak.
Yeah, sure, thank you. Sure, I mean, regarding your question, Beatrice, I mean, you have been asking about cleavage and everything. Actually, what we have seen in the mines, we have been going with Albert and what I've presented actually in the talk, is that really the anisotropy of the cleavage plane could guide actually the flow within the shear zone. So the schistosity is reactivated, at least in hydrothermal systems.
Thanks to the pressure of the fluid.
Yeah. Well, I mean, you might have a new stress field which occurs, which open veins in actually in homogeneous or competent basement. And when this vein is progressing through the vein, through this competent basement as it opens, and at some point it encounters something which goes across it or which is anisotropic, then this anisotropy modifies the track of the flow. At least this is what we observe for ore deposits. What I tried actually to show in my last slides, don't know if it's a matter of discussion.
Okay. Well, another question from the audience for the moment. What time is it? It's 2:00 noon. And on the very nice pictures you showed us, all these quartz veins, for example, were made during the same, not these ones. You skipped one picture.
I skipped this one.
Yes. For example.
This one?
Not this one. Well, this, yes, this one. And I wondered if
this one? Sorry.
There is a delay.
Yeah.
Not this one. The one on which the outcrop is rather black and there are many white quartz veins parallel to. There is only one. You have another one
on the exercise pages.
On
the exercise slide.
This one.
Yes.
And no. Which one?
No.
And I wondered if you had several events and how you can determine if there is only one event or 7 of them.
You mean for the first one?
Yes.
Oh no, the event is. I made a publication on that. No, it's multi-event systems. So the quartz vein, we are pretty sure, were developed as hybrid fracture before the folding. But during the folding, we had, but not everywhere, the sliding of one layer over the other by simply slipping along the bedding plane. And that happened really during the folding. But even you can see that some of the quartz vein seems pretty related to the axial plane. So the question is, are they related to the first event of extensional and hybrid fracturation, or is it a late event? Or even the quartz vein could have induced the localization of the fold structure. In other outcrop, I've even seen quartz veins that probably are related to the first events that were reopened as a tensile fracture at the hinge, the external hinge of some fault. So it's rather complex situation. And a quite complex structure to analyze.
All right. And what was the year of this paper? When did you publish it? You remember?
It's a memoir of the Geological Survey of Belgium. I can't tell you by heart like that, but let's say 2008.
Okay, thank you. Well, if
you want, you can get a copy.
Oh yes, please. Yes.
Okay.
Thank you, Yves.